In this video, we are going to talk about creating rational functions and applications of rational functions. So on this first page, we are going to talk about writing rational functions from specific information or given a graph. So if I look at number 1, they talk about this equation has to have a vertical asymptote at 4, meaning my factor is x minus 4. And if it's a vertical asymptote, it's in our denominator. They also talk about a removable discontinuity. This means if it's removable, it's a hole at x equals 3. So since it's removable, that means I have this factor on the top and on the bottom. In number 2, they talk about my end behavior asymptote is at y equals 2. Since my end behavior asymptote is at y equals a number, meaning it's the ratio of my leading coefficients, this means that my numerator and my denominator have the same degree. I also have vertical asymptotes at 3 and at 2. So I know that my denominator will have x minus 3 and x minus 2 to illustrate those vertical asymptotes. I know my numerator has to have an x squared because x times x will give me x squared in the denominator, and I know that my numerator and denominator need to be the same degree as I said over here. To make it 2, though, I'm going to have to put a 2 in my numerator because 2 over 1 would give me that end behavior asymptote at 2. In number 3, it says I have a removable discontinuity at x equals 5. So again, I'm going to have a hole at x with x minus 5 as my factor. So that means I have x minus 5 in the numerator and in the denominator. I also have a non-removable, meaning a vertical asymptote at x equals 0. So that's represented by just x in the denominator. I want to write a rational function with no removable, so no holes, no vertical asymptotes, and an end behavior asymptote at y equals 0. So if my end behavior asymptote is at y equals 0, that is a very specific one. That means that my degree of my numerator is less than the degree of my denominator. So if I have no holes or no vertical asymptotes, that means there's no value that makes my function undefined or no value that makes my denominator 0. So my denominator needs to be something like x squared plus 4 or x squared plus 5. I could put a 1 on top. I could have something like this. I could have something like this. Any of these would work. It just needs to be something where my degree of my numerator is less than the degree of my denominator. I have no holes, no vertical asymptotes. So any of these would work. In 5, they give me a domain saying that I have an excluded value at 1. And my limit as I approach positive or negative infinity is 0, meaning my end behavior asymptote is at 0. And so again, that means that the degree of my numerator and the degree of my denominator, my degrees are the same. But I do have a vertical asymptote at 1. Oh, I apologize. They're not the same. The degree, I wrote this backwards. The degree of my numerator, I was thinking degree, is less than the degree of my denominator. So I could have 1 over x minus 1. I could have a couple other things, but this would help me get my restrictions. All right, I have an end behavior asymptote at negative 4. Anytime it's a specific number, that means negative 4 is the ratio of my leading coefficients, meaning that my degrees are also the same. I also have vertical asymptotes at negative 1 and at negative 3, meaning my denominator will have x plus 1, x plus 3. And it must pass through 2, 0, meaning my x-intercept is at 2. So meaning when I plug in 0 for y and I set my numerator equal to something, it's going to equal 2. So that means x minus 2 has to be one of my factors. I also need another factor because I need both of my numerator and denominator to have a degree of 2. So I'll put x minus 5 plus 5 here, but this really could be any linear factor. I'm also going to put a negative 4 here because negative 4 over 1 would give me, I guess, this end behavior asymptote. In 7, they tell me my excluded values are 1 and 3, and that my end behavior asymptote is at 5/7. So again, this means my degrees are the same, and my leading coefficients are 5 and 7, or something that would reduce to 5 and 7. All right, so my denominator has to have x minus 1, x minus 3. I need them to be the same degree, so since my denominator would be x squared, I also need my top to be x squared, and I need my leading coefficients to be 5 and 7. Now I could have made one of these guys a whole by putting, x minus 1 or x minus 3 on top, because the domain just tells me that those points are restricted, not whether they're vertical asymptotes or holes. All right, I have an end behavior asymptote at y equals 0. So again, this means that my numerator degree is less than my denominator degree. No vertical asymptotes again, so this is going to be similar to number 4, where it had no vertical asymptotes. We put something in the bottom where it won't ever equal 0. And a y-intercept at 4. So that means when I plug in 0 for x, y needs to equal 4. So that'd be like something like x plus 4 equals y, because I plugged in 0. So I could have x plus 4 on top and x squared plus 1 on the bottom. I could have 4 on top and x squared plus 1 on the bottom. Either of those would kind of meet my criteria of having my degree and my denominator being bigger than the numerator, giving me that y-intercept of 4, and also giving me no vertical asymptotes. On the back, they give us a graph, and we're supposed to write the equation of this graph. So let's write down everything I know about the graph. I know that, let's switch to red, that I have a vertical asymptote at x equals -1. It's right here. I have an end behavior or horizontal asymptote at y equals 1. I have a hole at 1, 2. I have an x-intercept at -3. I have a y-intercept at 3. All right, let's start building from here. So if I have a hole at 1, that means I have x minus 1 in the top and the bottom because of the hole. If I have a vertical asymptote at -1, that means I also have to have x plus 1 in the denominator. Now, to get this end behavior of 1, this means that my degrees are the same, and the ratio of my coefficients is 1. But then I also have this y-intercept and x-intercept of 3 and -3. So if I put x plus 3 and then I plug in 0 for x, that would give me a y-intercept of 3. Or if I plug in 0 for y, it would give me an x-intercept of -3. So this factor is going to help me get those intercepts. And so this is what the equation of that rational graph is going to look like. All right, down here, we are looking at some real world problems, and we can solve a lot of this by hand, but we can also do a lot of this in our graphing calculator. So in A, it says approximately, well, it says the percentage of a drug that's left in a person's bloodstream after T hours is represented by this equation. Approximately what percentage of the drug is in a person's bloodstream after 4.5 hours? So 4.5 is our T. So I can just take 4.5 and substitute it in for T. and then plug this in my graphing calculator. So alpha y equals 5 times 4.5, and then go down 4 times 4.5 squared. I wanted to make sure that was in parentheses. So I'm going to get 0.26, well, I'll round this 1 up to 2, so 0.262. But as a percentage, that would be 26.2%. Now, how could I find this on the graphing calculator? Well, first, let's put this function into my y equals. So alpha y equals, I'm going to put in 5x on top and 4x squared plus 5 in the bottom. And since we're talking about percentages, we're talking about anything less than 1. So let's just adjust our window to the standard. But I can see that I only really need this kind of tiny part here. So I'm going to make my y a lot smaller. Make it -1 to 1. I don't even really need the -1, but. All right, so then to find out at 4.5, you would go to second trace, go to value, which is option 1. It's going to ask you what you want your x value to equal. I want it to equal 4.5. And it would tell me that it's 45 over 172, which I would need to put in my calculator. And we get the same thing I got above. In B, it says describe the end behavior. And then C says what's the end behavior asymptote. So actually, I would do C before B. So my end behavior asymptote is going to be y equals 0. And again, that's because if I look at my original function, the degree of my numerator is less than the degree of my denominator. So it's always y equals 0. So if my end behavior asymptote is y equals 0, that means as the limit approaches infinity, it's going to only approach 0. It'll never go less than 0. And so then what does this tell you about the amount of drug in the bloodstream? That the percentage will decrease towards 0 over time. D says at what time is the percentage the highest? So I'm going to look for my maximum point. So I'm going to go back to my graph. See the maximum's right here. So second trace, find the maximum. Got to get all the way to the left side of that maximum. Then to the right side of the maximum. Then guess. So at 1.118 hours, 0.559. So 1.118, 0.559. So at 1.118 hours, the percentage is at 55.9%. On what overall interval is the percentage more than 50%? So we're going to go to here, type in, I did not mean to get rid of that, 5x over 4x squared plus 5. And then I want it to be 50%, so 0.5, and then I'm going to graph. And I can see that from this point to this point is the interval that's above 50%. So I'm going to find this intersection point and this intersection point. So second trace, intersection, 1, 2, 3. So 0.69. 1.8. All right, let's go over this last question. It says a professor teaching a large lecture course tries to learn students' names. The number of names she can remember increases each week in the semester t. And it's given by the function n of t equals 600t over t plus 20. How many students' names will she know by the third week? So this is when t equals 3. So we can solve this two ways. I can just substitute 3 into my equation and solve. I could also type this equation into my calculator and solve that way. So let's do it both ways. Let's finish this way first. So I'm going to do 600 times 3, and I'm going to divide that by 23. So I get about 78 names she'll know about. We're going to approximate. I don't know why it's doing that. All right, so now let's type this into my graphing calculator. So alpha y equals 600x over x plus 20. I'm going to need to fix my window because I made it super small. So let's make it a standard window just to start off with. I'm going to need more window. So let's double this and let's make this a lot bigger because it's a 600 person lecture. So let's try that. I can see my line. And I want to find second trace when my x value is 3. And so I get 1800 over 23. So if I do 1800 over 23, that's exactly what I would have got here. All right, for B, it says how many students' names will she know by the end of the semester? So again, I could just plug in 16. And this should be 16. So she'll know approximately 266 names. I'm not going to round up because she hasn't learned the 267th name yet. So she's only learned 266 names. And again, I could have done that in my graphing calculator. If I had gone to my graph, second trace, what value do I want to know? I want to know when x is 16. Gave me 800 over 3. So it would give me the same answer. In C, it wants to know when will she know 150 names? So basically when, so I got to solve for t. And I could solve this a couple ways. I would actually make this a proportion and cross multiply. So I'd have 150 times t plus 20 equals 600t. 150t plus 3,000 minus the 150 over. I end up with 450t. So I'm going to do 3,000 divided by 450. About 6.67 weeks. Now, if I wanted to find that in my graphing calculator, I would put y2 as 150. So let's do that. And I could see where they intersect, and I would find that intersection point. So 6.67 weeks, and she would learn 150 names. All right, this last question says, according to this function, what are the most names she can remember? So we're talking about a most, we're talking about an end behavior asymptote. And if we look back at my original equation, I can see that the degree of my numerator is equal to the degree of my denominator. So my end behavior asymptote will just be the coefficient of my numerator over the coefficient of my denominator. So my end behavior asymptote will be 600. So therefore 600 names is the most she will be able to learn, which makes sense because it actually doesn't say it's a 600-person lecture, but I would bet it's about a 600-person lecture.